And what's happening?
I'm sorry, we just want to record it.
Okay. So, well, welcome to the people joining the recording. We forgot recording until now, so I hope you can catch on what I'm saying. Okay. So, what I was saying is, if the verifier can ask two questions, one out of two questions, then the prover may set up things to be able to answer one of them, but not both, because if it's a cheating prover, he cannot do that. And so there is a probability for a cheating prover of 1/2 to win this one iteration. So how do you make the probability better for the verifier? You just repeat. You do it one time, two times, until you get a good probability. Okay, but now if we move to the signature step, well, here, because the verifier is not really present, the prover could repeat this in his mind a lot of time. So we really want the probability of success of the prover for the global signing protocol to be very, very low. Otherwise, well, when I try to authentify in person, if there is one chance in a million I can win, you might say, okay, this is good enough for all reasonable purposes. But for signatures, this would not be good enough at all, because I could just go into my room, try 1 million attempts at signing, and then come out with the ones that did work. And that would take a little bit of computing power, but it would still be doable. So depending on whether the verifier is really there or not, the soundness, the number of questions, of total questions you can ask has to vary. Okay, and at the end, this is released. And now there is a verification process. And in the verification process, what happens? The verifier of the signature just, do as if he were the verifier in the original protocol. So he receives the commitment. Okay, he recreates the question, and then he does the checks that are here, the verification that were omitted from the signing process. Okay, and if it works, he accepts the signature, and everything is good. Okay. And you can extend this idea of fiat shamir with protocol with more than three rounds, with 5 or 7 rounds or whatever. But okay, it's really cleaner and easier to follow with 3 rounds. Okay. So I told you it really works very well for discrete log. So let's look at the case of discrete log. What is the base protocol for the zero knowledge? Here is, okay, what does the prover, so there is, of course, the public key y and the secret key x, with the relation y equal g to the x in some group where discrete log has to be hard, otherwise this is not very interesting. And then the prover does the following. He picks a random number r, and he creates g to the r, and he gives this as commitment. I will call h for this value. And now the verifier picks a question c in some range, whatever we want, basically. It just has to be smaller than the size of the group. Otherwise, questions are just modulo the group order. And the prover replies by sending this value s, which is r minus c times the secret. Okay, and how does the verifier verify? Well, it just checks this equality in the exponent by verifying that g to the s times y to the c is indeed equal to g to the r. And if this equality, if this holds, then this is going to be true. Okay, and basically what you see here is that if you can answer more than one question for the same commitment here, it means that you know s for 2 different values of c. So you basically know 2 distinct points on a line. This is a lot of information. Okay, and if the group order is invertible, you completely learn x. Okay, good. So when you turn this into a signature scheme, you can do it in 2 ways. You can do it in the stupid way I mentioned before, directly by, okay, you just output h, you let c be this value in the signing process, and then you output s. And this is a signature. And you can check it and there is no problem. Okay. But when you look at this signature, you have this here, which is a group element. And what happens sometimes is that very often the encoding of group element can be large. So it's kind of painful if you have to put a group element in your signature, especially if your group is large. It's better just to put smaller numbers. And this is done by a Schnorr signature. And in Schnorr signature, what's happening is instead of giving out H, the commitment of the prover, you give the question C. And why does this still work? Because of the verification procedure, you should be able to recompute H when the signature is valid. So what you do is you compute a temporary value H, HV equal what it should be if the signature is valid. And then you recompute the corresponding C for this value, and you check whether the two C's are equal. So now what's happening? Well, assume this is equal to H, then it's exactly the same thing as if we had sent H to begin with, so there is no problem. Otherwise, if this is not equal to H, but this is equal to C, so if it's still verified despite this, then you have a collision in the hash function. So in any way, something weird is happening if you are able to verify. So it should not work. Okay. And okay, so one thing is with discrete log, it's very cool because as soon as this is a random element, the S we are giving is kind of a one-time pad encryption of whatever you put next to it. So you really get perfect secrecy on X when you display S. And this is really nice. But sometimes you can think and design protocols where there will be a little bit of leakage. And this is something I don't want to speak about today, but which has been used, especially in lattice-based signatures, because if you have a protocol where maybe sometimes the question the verifier asks is going to leak a tiny bit of information on the secret, you might say as a practitioner, it's okay, it's just a tiny bit. But if you repeat and amplify your knowledge, you might lose it altogether. So, and the prover doesn't want that. But the cool thing is that because we are here, during the signing process, the prover can see that the question might leak something. And if it does, he says, okay, this is clearly a bad signature. I'm just going to forget about ever generating it, and I'm not going to give it out. And basically, you do some form of rejection sampling on your signature, and you can remove the leak. And this is called Fayad-Shamir with abort. And the only problem, that theoretical problem you might see with that, it no longer really comes from a protocol, because if you try to run the protocol, there is no way to erase the run completely. You cannot tell the verifier, please forget that I ever told that. This is not possible. Okay, this is leaky, forget it. No, this is not going to work because he will just take note of that, and just this simple fact will already be leaky. So we lose some of the neatness of the thing when we go to abort. Okay. So of course, until now, I am basically not in the topic of this conference because I have not given any single word about codes. So so it might be nice to try to go to codes. Okay, so in a nutshell, I just did try to put on this slide most there is to know about Stern identification protocol, which date back to '93 and uses code to do an identification scheme, and which you can turn into a signature by using Fiat-Shamir. So how does it work? So okay, so first, what is the hard problem we are going to look at? The hard problem is we have something H, which is called a parity check matrix for code. So it's a long rectangular matrix. And you have some secret value, S, which is a vector. So if you transpose it, which is why I have this T up there, you can multiply by the matrix. And you get some value, Y, which is called a syndrome. Okay, so far, this just looks like linear algebra. And it is linear algebra. So to avoid the problems being easy, you have to add some side constraints somewhere. And the side constraints you add here is the Hamming weight of S. So how many zeros and one, more precisely, how many ones you have in the vector. And usually you ask for S to have a low Hamming weight, and you want to know whether such a thing exists. Okay. And sometimes this is, when you see that for the first time, it's very surprising, because if I give you this problem, give me all the solution, forget about the Hamming weight, but give me all the solution of Y equal H times X give me all the possible X's. Well, this is easy. This is linear algebra. There is a full description. You get one solution, and you say the general solution is just one of them, plus plus a general solution in the kernel, plus a general solution of the homogeneous equation. Okay, so you have all the solution with a very compact representation. So what's the problem? Well, the problem is you have them, but you have them with a description that doesn't tell you anything about the Hamming weight until you go really generate one of the elements in your full vector space, well, affine space, and look at its Hamming weight. So now you have this huge space, which is linear or affine, but you need to find this low Hamming weight element in it, and this is where it's difficult. Okay, so we have this hard problem, which is proved to be NP-hard, so it seems to be quite strong, and we want to do an identification scheme out of it. So how do you do it? So, well, we are going to use one part which is going to be the same trick as in the discrete log. So we pick a random element, and we are going to multiply the matrix by this random element to get some commitment. Okay, this part is reasonably easy because we did it in discrete log. But we want some way to carry the information about the Hamming weight. So some side information. So to do that, you pick some random permutation sigma, and we are going to see how it works. So you pick these two values, U and sigma. You compute the syndrome corresponding to U by multiplying U transpose by H. You concatenate this with sigma, and you commit to this. So just take any hash function you have in your toolbox, compute a hash value of this, and give out this. You also commit by producing a hash to sigma of U and to sigma of U XOR S. Okay, so this is what you do, and you send this three value to the verifier, and now the verifier has three questions you can ask, 0, 1, or 2, and depending on the question, you are going to give different things. So if the question is you get is 2, you give sigma on U. If the question you get is 1, you give sigma and U XOR the secret. If the question is 0, you give sigma of U and sigma of the secret. Okay, and what you do is, well, when in this case you check that the Hamming weight of sigma of S is the thing you are expecting, because permuting a vector doesn't change the Hamming weight, so you can still verify it. And you also check these commitments, at least the one you can. So with question I, you can check all the commitment except CI. So let me just show you. If you have sigma on U, you can check this thing, you can check this. You cannot check this one because you don't know S. If you have sigma on U XOR S, you clearly can check this. This one is no, you cannot because you don't know S. And this one you can check because you multiply by this by H, and you add the Y, which is public, to cancel the contribution of S. Okay, so you can check too. And in this final case, You also can check two. This, you can check this directly, and you can check this because this is the XOR of the two permutations by the linearity of permutation. Okay, good. So, so these are the three questions. These are the checks. So now what is the probability if I don't know the secret that I can check? You might say there are three questions, which would be 1/3. Well, no, bad, it's 2/3. And why is it 2/3? Because there is a strategy that whatever that permits me to create something that is fake, but that let me answer two questions for any choice of two questions you give me in advance. So if I want to be able to answer 0 and 1, I will generate the commitment that way. If I want to answer 0 and 2 that way, if I want to answer 1 and 2, I will generate that way. So let me be a little bit more precise. So I create two fake secrets, S prime and S second. So S prime has the correct Hamming weight, but whatever syndrome. And S second has the correct syndrome, but no good Hamming weight. And this is easy, remember, just linear algebra. And now if you look at this, you can look at what I have committed to and find out what are the answers that I can give. And so basically, I will just give the answer where S is that are asked from me, where S is replaced by the corresponding thing. So either S prime or S second, and it's going to work. So, well, typically, let's look at the last one here. I want to be able to answer question 1 and 2. So if I am asked question 0, I should be in trouble. So, well, clearly, if I am asked question 0, someone is going to check the Hamming weight. And the Hamming weight of this is bad. So I am in trouble. But if I am asked question 1, so question 1, what do I want? I want sigma and some value, okay, XOR S second. And someone is going to check that the syndrome are correct, which they are, no problem. And for question, if I am asked question 2, I have to give sigma and U. I know them, so no problem. Okay, and you can check for all of them that you can indeed cheat with probably 2/3 in all these configurations. Okay, so it means that if you want to use that into a signature, you have to repeat quite a lot of time. Okay, depends on your security level, but if you want a probability of cheating of 2 to the minus 100 or something, you will have to repeat probably something like 200 times. And of course, the more you repeat, the more information you have to pack in the signature, so the longer the signature will be. So this is why this gives signatures, but they are quite good. Okay. Okay, so now the problem is, well, we would like to have code-based signature, but we would like them to be smaller. And there is this very, very cool idea that I want to discuss, which is MPC in the head, which is multi-party computation used in this context of zero knowledge. And initially, this was introduced in this paper by Zero Knowledge from Secure Multi-Party Computation by Ishai, Kuchilevitz, Ostrovsky, and Sai. And basically, the idea is the following. Let's assume you have any NP relation. So you have some relation R, which you can verify in polynomial time. And you have two arguments, a value X and a witness W. And you want to verify that the thing goes together. So in discrete logs, this would be the value, this would be the log, and you want to check that the two things work together. And with code-based, this would be the syndrome, this would be the secret, and same thing. There is an easy way to check. Okay, so the idea was the following. Okay, take the witness, which is secret, and split it into a multi-party computation between many people, so n people. And so you have this split where the witness is going to be the XOR of all the shares of the people that have that commonly hold the witness, and you will still have the same, the public argument will of course be the same. And now you take a multi-party protocol that can verify this. And people that work in multi-party computation have worked a lot, and they can do that for any NP thing that you want. And now the idea is, okay, what you do is you have your prover, and the prover is going to run this multi-party protocol, but not with real parties. Instead, he's going to do the split of his secret and then run this using virtual parties. And he was going to keep track of all the computation and all the outputs that are produced during that. And he's going to commit to the view of the people that participate in the protocol. Okay. And now, once he has committed to this, you recognize the first step of committing in the zero knowledge part. The verifier is going to say, okay, good. But now I want to verify that what you are doing is reasonable. So I'm giving you some of the parties, and you have to open them and show me that everything they did was correct. And what they showed is that just by opening 2 random parties, you get some soundness, which is small, and by repeating, you can create a zero knowledge identification protocol just from this multi-party. Okay, good. So this is quite old. It dates back, well, depends what old means, but dates back to 2006 or 7. I always forget the date, but good. But now this was really thought to be something more theoretical. And at some point, people started to realize, well, it's not only theoretical, it can be very nice in practice. And basically, it started with the Zikebu paper, where they showed that you can, in practice, do lots of Boolean circuit efficiently with this multi-party computation in the head. And well, if you can do arbitrary circuits, you can do anything. You can do secret key encryption. And people had the idea, which is the picnic family of, well, let's take secret key encryption and prove that I know the keys that would encrypt 0 into this value for this crypto system. And if I can prove that, then I prove I know the secret, and it will still be hard for anyone else to find. And that might give nice signature out of a very symmetric key primitive, which is kind of counterintuitive because signature are supposed to be something public key. So that was a very nice progress. And but these practical aspects are much more recent than the theoretical aspects. Okay. And there are lots of papers. Okay, but that's where what I said in the introduction come by. It's still hard for me to try to wrap my mind around all this, because you have this protocol, this multi-party protocol that you have to keep in mind that does the thing, and then you put it into the zero knowledge proof, and it's too complicated to follow. So in order to make it simpler, I decided to do something that might seem completely useless, because I'm going to use discrete log to illustrate this. And of course, discrete log is not going to be post-quantum secure. So, but at least it helps me, because the verification protocol here, the multi-party protocol, is so simple that you don't need to worry about it to be able to look at the in the head part. So the multi-party itself is going to be out of the way because it's so simple. So, okay, so let's see. I have my secret X, and I'm going to do an additive sharing, X equal X1 plus X2 plus Xn. Well, not XOR, I'm not going to do a Boolean additive, but I'm going to do additive in the group order, not Q. And I'm claiming that if I have parties that hold each of the party hold one of the Xi, it's very easy to collectively verify that the sharing is correct. How do you do that? Each of them just compute X to the X1, X2, Xi, Xn, and output this value. Okay. And then everyone check that the the product of all the output is X, is Y. And if the product of all the output is the thing, is the right target, then clearly the sum of the inputs, assuming that they all behave nicely, the sum of the input has to be the discrete log. It's just plain stupid. Okay, good. So now that this protocol is so easy and that everybody can remember it easily, let's look at how it turns into a signature by using the multi-party computation in the edge paradigm. So first, I'm going to do it in the most stupid way. So I'm just going to run the protocol and just print everything. Okay, these Y's by themselves are already commitment. So I can just print the full view of everybody and include this in my signature, in my identification scheme. And then the verifier is going to tell me, okay, maybe I trust you, maybe not. So I'm going to ask you a question I, which is one party number between 1 and 10. And what the prover is going to do is going to answer by giving out all the value of X except Xi. So you give everything except for the position that correspond to the question. And what you do then is you check that for all the J not equal to Y, not equal to I, sorry, Yj equal X, G to the Xj. So you verify that these things have really been created from known logarithms. And you check that the product of everybody is indeed Y. Okay? And if you do that, what is the probability for the prover to cheat? Well, if I succeed for one of the questions, then I have to know the logs of all the Y's except maybe one. Okay, so on this one, I clearly have to cheat because otherwise I would know the log of Y. So I can cheat by just replacing the values that I want to cheat on by Y dividing by the product of the others, and then this equality will check. All these things will check, but if someone asks me to reveal Xi, I wouldn't be able to do it. Okay, so in that case, it means that I just have one chance in N not to be asked the question I cannot answer. Okay, so it's pretty good. One chance is N in N. But you see, it's still very worse than the initial thing we had. Because the number of questions is limited by the number of parties we can put in the computation, so by the running time you want to invest. And this is why these signatures are not going to be as good as Schnorr signature or this kind of thing for discrete log, because they are going to be longer. But still, what I have displayed here is the stupidest thing. And it's not using any of the nice tricks that are available for MPC in the end. And I want to start from this and show you some of the nice tricks on this example, because since it's easy to keep in mind, it will be easier to see the contribution of the nice tricks. Okay, so first thing is here, this is very long. This is N group element, so my signature is going to be huge. And I have to repeat on top of this. Doesn't make sense. So instead, what you can do is an implicit trick, like we have already seen, but I'm going to revisit it here. So what you do, instead of sending all these values Y, you just send the hash of them. So now you go from a very long thing to just a single hash, which is short. So nice for the signature. The verifier sends the same thing as before. And now you send all the Xi except this. But the Xi are exponents. They might be smaller than group elements. So it's not the worst part. So you send all the Xi's except, and you compute all the Yj, which you can compute. And you compute the missing Y, the missing one, by using this verification relation. you take the target value big Y and you divide by all the things that you were able to compute before. You put back all these values in the hash function and you check. So either everything is okay, in which case it's equivalent to what I showed before, or not everything is okay, and then there is a collision somewhere. So in any case, it's like when we transform the ordinary signature to Schnorr signature, we use basically the same trick. Okay, so it's better, it's shorter, but still revealing all these xi is costly. And that's where the next trick comes in. And the next trick is very, very cool. So the next trick is something that uses Merkle trees to compress all these xi's into something much shorter. So you have this so first thing, it's way easier to do if all these elements are pseudo-random. But if you take all the xi to be pseudo-random, the sum of them is not going to be the right value x that you wanted. So we slightly modify the equation and rewrite it by saying that x is going to be, okay, all these x that comes from random value plus some offset. And we will have to reveal the offset somewhere. So all the parties just know random things, basically, but there is some offset to correct it. And you have to include the offset everywhere in the verification relation and stuff, but that's really easy. So now, how do you make sure that we can send all these values except one for a small cost? And in order to do that, you create this value in the following way. You start from a random value, which I call the root seed, and you use two derivation functions, left and right, which you can get from hash function. You can do hash of left concatenated with the value and hash of right concatenated with the value, and this will give you the two derivation function. And now you get S0, S1 from this. From S0, you create S00, S01. From S1, you create S10, S11. And clearly, you can do a full binary tree as deep as you want, just by going left, right, all the time. Okay. And at the bottom of this tree, you just have random value, which I renumber from binary S000 up to S11111 into my ordinary numbering from 1 to 1. Okay, so clearly, it's nicer if n is a power of 2. Okay, good. And the very nice trick is that now you can send for any choice of position you do not want to send, you can send all of the others for logarithmic cost instead of a linear cost in their number. And how do you do that? Well, assume for simplicity that I don't want to send the last value. How am I going to do it? Okay, I cannot send the root because if I did send the root, I would send everything. But I can send S0 because it only generates the left part of the tree, which doesn't contain the value I want to evoke. Okay, now here I cannot send this because it would generate everything, but I can send this one. And at the next level, same thing, I can send one value. So at the first level, I send something which reveals half of the tree, the half where the value I don't want to reveal is not. At the next level, I reveal another value, which gives another half of the remaining half, and so on and so forth. And clearly, by revealing one value at each level except the root, I'm just revealing everything except one value that I wanted to evoke. Okay, and this really compresses the thing a lot, because now, if you look there, this has been compressed, and now this is also compressed. And with these tricks, well, the signature become quite nice in terms of size. Okay. But still, because n is large, well, n has to be quite, the larger n, the fewer the number of repetition. If you just take n to be 2, then you have to repeat many times. If you take n to be bigger, then you have to repeat. But in any case, you still have quite a lot of computation to do here. the number, you still have n computation to do, n exponentiation and all these things, and this is quite costly. Okay, so we would like to work on this and try to improve these computations and do fewer while still keeping the same MPC in the head format. And this is where there is a very nice trick. Okay, I forgot to, I think where are they? Where did I put my, no, not my notes. Okay, I wanted to display the reference of this paper, but somehow I have lost it. I made a bad copy paste and destroyed it, sorry. Okay, I apologize especially to the authors, but yeah, sorry. So this hypercube technique is really cool. So you still take 2 to the n values, but now instead of viewing the binary tree just as something flat, you reorganize it into an hypercube. So, well, you basically all know what an hypercube is, especially with okay. Dimension 1, I just take 2 values like this. Dimension 2, I take a square. Dimension 3, I take a cube with eight nodes. Dimension 4, it's becoming hard to draw, but you have these 2 cubes, one now and one in 1 minute with 8 and 8 things. And with higher dimension, it's getting messy to visualize, but you can see you have this hypercube. Okay, and now what you do with the hypercube, you take, there are lots of directions. So if you take the square, you have 1, 2 possible direction of faces. If you take a cube, you have 1, 2, 3 direction of faces. If you take a dimension 4 hypercube, you have 4 directions. And more generally, if you go to an hypercube of t dimension, you have t distinct directions. And now what we are going to do is we are going to choose one of the directions, and we are going to reinterpret this sharing, the global sharing of X, into many different smaller sharings. And how do we do that? We simply group by taking the sum of the shares over the sides that correspond to the direction. Okay? Do you see what I do? So if I have a square, I could either take the sum of these 2 things and these 2, or the sum of these 2 and these 2. But with the square, it will not be efficient because the log is not going to kick in. But with a cube already, instead of having 8 values, you will have 1, 2, 3, 4, 5, 6. Okay, and you group them like this by summing over one side on the other side in the same direction. And now clearly, because I'm just grouping stuff in the sum, for any value of I that I have chosen, I have one split of X like this. So I can do one instance of the MPC in the head with 2 parties for each I. So in fact, what I can do is T instances of the MPC in the head for the with 2 parties at the cost of this thing. Okay. Well, now if you look at this, you are going to tell me it's exactly the same thing. I am running T protocol with 2 parties instead of 1 with 2 to the T party. I have the same soundness, the same tree to share, the same thing. Where do I gain? And the place where you gain is that adding values, mod Q, is much less costly than computing an exponentiation. So everything stays the same, but the number of exponentiation we compute goes down from big N to a small multiple of T. Okay, and this is where this also helped in the code-based setting, and you can use this hypercube technique to get better signatures than when you don't use it. Okay, so and with all these things, well, people have been proposing plenty of schemes. So there is one missing because I wanted to move it to the previous slide, and I just, okay, I made a copy paste stupidity and lost it. Okay, but believe me, this hypercube thing is quite important, and yeah, but you can also find all these things in. Okay, so the only thing I didn't explain, and I think I'm running short on time, but so I'm not going to do it fully, is how do I do the MPC in the head for code base? And there are two parts in the code base. There is computing the syndrome part, which is easy because it's linear and it's exactly as in the discrete log and everything is easy. But computing the Hamming weight is more difficult. And basically, there are a few ways. The standard one is to use polynomial, what are called support polynomial, and verify polynomial equalities. And you have to verify a product of two polynomials, and it will work. And the other thing that is quite cool, but if you are interested, you want to go to the talk of Eliana at Eurocrypt this week, and which is if you have a sharing of S, not mod 2, but over the integer, let's say, then you could check the Hamming weight simply by just adding the coordinate and verifying that the number is indeed 32 or whatever you want it to be. Okay. There are lots of tricks because you have to check that these things are really commitments of bits. So there are lots of things to take care of, but the basic idea is that. And for the multiplication thing, the basic idea is that you can multiply, you can verify multiplication of values and then of polynomials using something called as beaver triples, but it makes the protocol a bit more complicated also. Okay, and of course you can do tons of other things with multi-party computation in the head, and this is just the surface of it. People have been doing, private set intersections. They have been doing, okay, whatever you want. They have been doing some Bitcoin stuff. They have been doing verifiable encryption and so on and so forth. So it's a very cool technique, and it's developing extremely quickly. Look at the dates I have in all my citation. Everything that's from, last year, 2 years ago. It's extremely active and quite nice. Okay, so